Hello, my name is Bob D. Hilster, and I am your particle model guru. Today we're going to talk about the solar eclipse. This is the second and last part where I try to explain what's happening. And at the end of the last video, I listed all these things that could affect it. It makes it very difficult to get identical eclipses. Very difficult to try to explain it. In the past, I've used the corona and the halo and shielding, the fact that G1 particles are lost as they pass through an object. I use those two to explain it, and this time I'm going to add the G1 particle and G2 gravity. So I'm going to review the G1 particle for a while. This is a bit of a review first. The G1 particle is not a solid particle. I say particle all the time, and people seem to think it's a solid particle, and it's not. It's porous. I'm suggesting that it is made from subatomic particles. That's what makes it porous. The only way that a mechanical model can have an object put together and be porous, like to the extent that we say it, is to have subatomic particles below it. And of course, the G1 moves at or about speed c. I've talked about the G1 particle field. This field is generated by the emission of G1 from all the stars, including our sun. They can also be generated by streams of G1 light colliding, causing the G1s to scatter. So as light paths cross in space, you'll have the occasional hitting of G1 on G1, and they literally bounce and scatter off of each other. G1 particle field. Then there's G1 gravity. It occurs around an object when the G1 particle field passes through and interacts with the object. And it can do three things. It can pass all the way through, it can interact and scatter, or it can get trapped as an orbital. Since there are more entering the object than leaving, there is a net force of acceleration that exists around the objects. And this net force is generally known as Newtonian gravity, which I call G1 gravity. G1 light. G1 light is emitted by the stars in the forms of streams of G1s that have a repetitive pattern. Many G1s here, very few here, many G1s there, and it can be at different wavelengths. So we have G1s moving at speed c. We have G1 gravity moving at speed c, but the differences in how they're organized. G1 gravity is not organized like this, but G1 light is. And then there's a G1 magnetic field. It's made up of many G1s moving around and through the magnet. It is a high-intensity stream of G1s that is controlled by G2 gravity. This makes the magnetic field look like a strong version of G1 gravity. Think about it. The same particle, magnetic field, is a strong force. Gravity, G1 gravity, is a weak force, and it all depends on the intensity. And in this case, the magnetic field looks like a strong version of G1 gravity. And then we introduce G2 gravity is responsible for causing G1 light to turn as it enters a prism. That's how I determined that there could be a G2 gravity. And it also causes G1 light to turn as it passes the sun. In a sense, it's causing refraction. Since the G1 field, now here's the key point, since the G1 field is made up of streams of G1s, and if they pass by the sun, then G2 gravity can also turn a G1 gravity stream. So this is something that I didn't have when I first tried to explain the Wang Eclipse and the Allais anomalies. So in my paper of 2012, I explained the bumps by saying that the G1 passed through the corona or halo and through the moon and reduced. It caused the bumps, and this caused the bumps, but I was never able to explain the middle part of the Wang eclipse. But I could explain the Allais anomalies using that concept. So these are the assumptions I'm making in order to explain this. The sun is stationary. Of course, we all know that. It's the Earth and the moon moving around the sun. The Earth and the moon move together. Well, not precisely. The Earth is spinning spinning towards the east faster than the moon is orbiting towards the east. And in general, the moon looks like it's moving very slowly to the west. But for the difference is small for this purpose, so I'm assuming they move together. And as they move by the sun, we have the same thing. We have the I'm going to try. This is the a meter or the pendulum, and this is the Earth, and they're just moving slowly by. Back in Newton's time, the speed of gravity was considered to be instantaneous. Kepler thought the speed of light was also instantaneous. With these assumptions, Newton's gravity equation works, and I'm positive today that when astronomers take a look at the sky and they want to measure where a planet is and what its direction and velocity is, they assume that what they see is where it is. And when you do that, you're assuming the speed of light is instantaneous and the speed of gravity is instantaneous. With these assumptions, Newton's equation works. They do their measurements and they use Newton's equation and they get very good results. But this is my opinion. Because the speed of light and gravity are about the same, then maybe they are the same particle. Maybe that's how I came to the conclusion that the G1 gravity and G1 light were made from the G1 particle. And in this case, when they both move at speed c, you can show that Newton's equation still works. So we're going to look at three positions: just before first contact, at totality, or when there's maximum coverage of the sun, and just after. So let's take a look. So here on the left we have the sun. It's fixed. We have the Earth and the moon moving together, sliding this way to the maximum and then on over to the end. And we have G1 gravity flowing through towards the Earth, and down here where we have the gravimeter or the pendulum. Now there's a path right here that I show, or two of them at least, that should come down this way, but because they're passing through the halo and the corona, they are bent, creating a gap. And I thought, aha, I got the answer, and I went on from that. I took this part, blew it up so it's a little bit more clear. If you're missing these streams, then you have more force on this side than this side. These arrows are supposed to be in line up here, but it gets a little bit crowded, so I put them outside. And you can look at the vertical and horizontal forces. This has a stronger force, this has a weaker force, and so the net vertical force is somewhere in between. You have a vertical component of this and this one, and so you have a vertical force that is smaller than expected because of this gap, which is what causes the bump in Wang's eclipse. As far as the pendulum is concerned, the pendulum doesn't worry about the vertical component, it worries about the horizontal one, and the horizontal component of this vector and the horizontal component of this vector give you a net force towards the left, which can push the pendulum exactly the way Allais saw it. The only problem is that after I drew all this, I realized, wait a minute, there may be more to this bending than I'm showing here. This makes a nice, neat explanation, but what if there's a stream of particles over here, which is kind of coming out this direction, but hits the corona and bends and replaces this? So in fact, you can have a whole stream, a bunch of streams of particles coming through, hitting the corona and bending and kind of creating a flow of different streams all the way across through here. Well, these might actually get replaced. There may not be this type of gap because of the other streams that replace them. If not, I'm still left with the fact that you have the halo and the corona that can shield and reduce the G1 flow this way, reduce it as it passes through the moon, as the moon goes into this gap, and still get the same result as far as these forces are concerned. So that part may still hold in this, analyzing these forces. Creating this gap may not happen. Same thing on the other side. You can go through the whole spiel again. However, you have a vertical force, a reduced force in the gap, and this time you have a force the other way. But the same thing happens over here. You can have more that replace it, and so you're left with the corona, the loss through the corona and the halo and through the moon to the Earth, giving us a similar effect regardless. But here's the amazing part, the one part I couldn't explain before, and that is that when the moon and the Earth, when the moons and the Earth is below the sun, you have these paths coming this way. You got a whole stream of these things being spread around through here and through here, creating more and more particles coming in the middle that you would not expect to have. See, the bumps are so-called anomalies, but the part of the anomaly is that this is supposed to be lower. These streams that are bent around and come in this way can actually bring this value back up again. Does gravity 2 help? Because of all the different conditions surrounding the eclipse, it's difficult to duplicate the measurements made by Allais and Wang. That doesn't mean that scientists should not try to explain these discrepancies. Gravity 2 seems to give more possibilities in general and may give more than I'm saying, but especially during the main part of the eclipse, it may explain that part of the Wang measurement. My name is Bobby Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.